All right, welcome to PyTexas first afternoon. We're going to be looking at the magic behind descriptors, descriptor protocol. We are going to try to unlock this for you to understand, at least at some level, what is going on with your Python code every day. But first, let me give you a quick introduction to me. I work for Bloomberg Engineering, in case you can't tell. I joined Bloomberg in 2014 as a software engineer. During my years there, I have been in individual contributor roles. I've been a TL, and most recently, I have been a full-time technical trainer. I have been a leader in the Python Guild. This is an internal Bloomberg organization since 2018, and I am a emeritus chair of that organization. And one of our current chairs is right in front of me. In addition to what I've been doing at Bloomberg, I have off and on been involved with O'Reilly Online and have done Python education through that medium. So why did I do this talk? And it boils down to curiosity. At an internal event, one of our other engineers did a 5-minute lightning talk on the descriptor protocol, and I went, wait a minute, I don't know anything about that. How did I not know that this thing existed? And so I started digging in, and I discovered that descriptors are everywhere in Python. So I'm throwing this term around, descriptors, so let's define it. Well, a descriptor is any object that implements the descriptor protocol. What could be more obvious? Okay, so what is the descriptor protocol? It is the mechanism for attribute access on an object. So the descriptor protocol enables objects that are attributes of other classes to customize their behavior when they are read or modified. The protocol consists of 3 methods, and I'm going to be using the word dunder a lot here. Dunder means double underscore, so hopefully we'll have some clarity there. The 3 methods are dunder get, dunder set, and dunder delete. There are 2 types of descriptors, and we're going to see how this affects attribute behavior. What is called a non-data descriptor implements only the dunder get. Okay? If I implement either of the other 2 methods, dunder set or dunder delete, then I am a data descriptor. It is very common, but not required, that a data descriptor also implement dunder get. And as I said, descriptors are everywhere. So non-data descriptors, any method that you define on a class, when you access that method, you are accessing a non-data descriptor. Anything you decorate with @class method or @static method, though you're creating a non-data descriptor. Methods on built-in types, things like list.append and dict.items, those are non-data descriptors. The super object is a non-data descriptor. For data descriptors, if you've ever used @property, you've created a data descriptor. Or if you have defined attributes via dunder slots, you have created data descriptors. So whether you knew it or not, you've been using descriptors pretty much from when you started writing code in Python. So I'm going to give you a very simplified view of how attribute lookup works in Python in terms of the descriptor protocol. So if I have an object, obj, and it has an attribute, attr, when I ask for that attribute off that object, Python will look on the class to see if there is a data descriptor by that name on the class. If it doesn't find that, Then it will look in the object's local dunder dict, where attributes are normally stored. If it doesn't find it there, then it will look for a non-data descriptor, again, back to the class. And if that fails, then I raise an attribute error. I couldn't find it. Now, this, of course, is a simplified view. If we look at this a little bit more expanded, is that actually, when I look for data descriptors, I not only look at it, the class, but all my parent classes that are involved in that object. But I start at the class, I look for data descriptors, then I come to the object, looked in dunder dict, and then I go back to the class, and I look for class attributes or a data descriptor on the class or any of its parents. MRO, for those that have not seen this term before, means method resolution order. But again, if I don't find it in any of these places, then I raise an attribute error. So that's a lot of words, but it makes more sense to look at this in code. So giving a public talk is not hard enough. So we've got to inject a little bit of live coding here. So we have two files here, demo.py and squeaky.py. And what we're going to do is we're going to write a squeaky descriptor that's going to basically print out where we are in the code. So let me grab my squeaky descriptor, because you don't all want to suffer through my slow typing. So this is a descriptor. It implements a dunder get, so it is a non-data descriptor. And the part here that I want to emphasize is this print, that it's just going to, like when dunder get gets called, we're going to print out something. And because this is a non-data descriptor, ultimately we have to store the value somewhere. And we're going to store it in this attribute underscore squeaky. And if we don't find that on the object, we're going to just return some default value. All right, so let's implement our code here. So I'm going to use our import. So from squeaky import squeaky descriptor, and I'm going to make my demo class and I'm going to create an attribute A that is a squeaky descriptor. So now I have this. So let's start up Python. And I have to be in the right directory. There we go. Yes, I do. There we go. And here I'm using -i. This is just going to read in demo.py and then put me at the interpreter prompt. So it just becomes a quick way of getting to the REPL, but having my demo class. So I'm going to create an instance of my demo class. And I'm going to type it correctly. All right, so now I have my demo class. Now my demo class doesn't have an attribute or doesn't have a value set for my attribute A. But when I access that, what it's going to do is it's going to notice that A is a non-data descriptor. It's not a data descriptor. And it's not in my dunder dict. So then it's going to go look and see that, oh, squeaky descriptor is a non-data descriptor, and it's going to pull back the default value. Now, if I set this to some value, now when I look at the dunder dict, I have my value A there. And now when I retrieve z.a, I'm getting the hello, because now the dunder dict is being found first. So remember the lookup order is I start with a data descriptor, but in order to be a data descriptor, it has to have dunder set or dunder delete. This one doesn't, it only has a dunder get. So then it goes to the objects dictionary and it finds it there, and we're done. And notice that we did not squeak here. All right, so that gives you a vague sense of what a non-data descriptor would do. So let's look at what if we change our descriptor from a non-data descriptor to a data descriptor, right? So I'm going to define a dunder set, and the dunder set is also going to be looking for this value in this dunder squeaky. Since I've redefined my class, I'm just going to quit out of here. Ooh. Yeah. Thank you. And let's get our instance back. Right, we still don't have our A in here. So if I do z.a, I still get the default from before. If I do z.a is assigned, hello, that squeak is coming from the dunder set. And now if I look at my dunder dict, it no longer has the A attribute, it has the dunder squeaky, because that's where my set method, my dunder set method, put it. So we're seeing a little bit of the difference between the non-data descriptor and the data descriptor. All right, so let me make sure we covered all of this. Right, so this is all well and good, but there's a problem. My descriptor is actually a little bit broken, because if I add a second squeaky descriptor to my class, and I read it back in, if I get an instance of my class, z.a, right, squeak, so let's do, and z.b, squeak, so I go z.a gets, well, let's assign hello again, and then I go, well, let's double check on what z.b is, and oh, it's no longer default, it's hello. And how is that happening? The problem is that I'm using the same location to store the value. So if I say, well, z.b shouldn't be hello, it should be 42. All right, that looks right. But now A is 42. And it's because both descriptors are referencing underbar squeaky. So what we actually need here is something that I haven't told you about yet. So one of the things that was introduced in Python 3.6, I believe, is support for getting the name of the attribute that the class is assigning my descriptor to. And that is dunder set name. So we need this added to our descriptor. So the key thing here is this name is the name of the attribute that this object is associated with in the class that it lives in. Owner is the class. In this case, I don't actually need the class, but I do want the name, because now instead of using underbar squeaky, I'm going to use self.name. So let me Actually, for me, this is just faster to do this. And one more place. Right, so let's get out of this. Come back in. Now notice that we squeaked just loading the class. So set name runs at, under set name runs at class definition time. So now my two instances of my squeaky descriptor know what their name is inside the demo class. So now if I do z.a equals hello, well, it would help if I had a z instance. There we go. Let's do that again. Right, so I get the squeak, and if I look at z.b, it's still the default. And so now if I set z.b to 42, and I double check what z.a is, it is still hello. So I've gained that isolation. All right, so this is all kind of interesting and potentially useful, but let's actually use this in a real implementation. So what we're going to do is, instead of having this toy example, let me open this up. So I'm going to define a point class. And the basic idea here is that I want to be able to define the point in Cartesian coordinates in x, y, but I want to be able to get the polar coordinates whenever I need them. So I'm going to define this r method and the theta method that are going to allow me to get the polar coordinates. And this all works. And if I come over here to my Python, and at this point I'm just going to run it. So whenever I access the R, the radius is calculated and I get the value. I update the x value to, I change it from 3 to 5, and I recalculate the radius, and everything works. But the problem here is that in my point class, when I want to access the x attribute, I can just do .x. But when I want R, I have to call it like as a function because it is a function. Well, there's a built-in way in Python to get around that. And so now I can turn my function into a property. And now I can, instead of calling it as a function, I can use it like a regular attribute. And everything still works. But let's just say that we're doing this a lot. We're not changing the x, y values very often, but we're calling R a lot. And now the computational time is starting to build up. And so I want to cache the R value so that I don't have to keep recalculating it all the time. Well, again, Python provides us a nice way to do that. So from functools, import cached property. And I can just change this from property to cached property. All right, so I have a nice cached value. But now I have a problem. When I change the X value, cached property doesn't understand that the cache has been invalidated. And so I can't use the built-in descriptor that I get from property or cache property to get the two things that I want. I want on-demand calculation, but I also want to cache the value as long as the inputs haven't changed. So what we're going to do as an interim step is we're going to introduce a cached property that's going to replicate what @cache property does. And then we're going to go back and we're going to fix this. So let's get our cached property. Right, so this is a cache property. This is going to do our under set name. It's a non-data descriptor, and we're going to leverage that. And it's going to keep track of the compute function. So this works exactly the same way that the built-in cache property works. So we're just kind of replicating the behavior right now. And this naive implementation has the same problem that the @cache property has. But now I have something that I can work with. I have this descriptor that I can work with. And what I'm going to introduce, the problem is that the cache doesn't know what its dependencies are. So what I'm going to do is I'm going to introduce to this descriptor a set of dependencies. When I create the cache property, I say, oh, by the way, if these things change, you need to update. And just to make sure that I don't misspell something, let me bring this over. And the other thing that we're going to need is a way to invalidate the cache. Right, so now I'm starting to build up some behavior that I'm going to get from my attributes, and I need the descriptor protocol to do this. This is the point here. The other thing that I need is a way to signal the invalidation. And so I'm going to introduce this other descriptor without a whole lot of explanation. That what it does is I can assign which attributes are going to cause the invalidation. So if I go back to my point class, this now becomes, let's pull in my invalidating attributes. And what I'm going to do here is I'm going to say X is an invalidating attribute. So is Y, because these are the ones that cause the invalidation. And then I'm going to redefine R and theta in terms of this cache property, and I'm doing it as a function call because I could do it as a decorator, but then we would have a lot of obfuscating code in here, and I want to focus on the main point. And so what this is saying is that I want to recompute the cache, or I want to invalidate the cache if either X or Y changes. need this here. All right, so now, and we're almost done. No parentheses, oh my goodness. Okay. What's that? No pressure. Oh yes, thank you. Like I said, doing a talk is not hard enough. Did I leave something out? Okay, so I'm going to just... What's that? Okay. D? Okay, let me... There we go. All right. So I'm not sure what the typo was, but so in order to get this behavior, I had to go into the descriptor protocol. So now I'm getting both the cached property that I could get kind of for free, but I also am getting the validation. All right, so just a quick summary of what we're doing. I've actually glossed over a few details in what happens in attribute lookup. It's actually more complicated. This whole process is orchestrated by something called dunder get attribute that you can also override. And there's some more details in here. The one that I will call out is item 5, is that there is a fallback mechanism that is implemented by dunder get adder. It is very easy to get this wrong, so here be dragons. I did not talk about the lookup order for set. It's simpler. It's orchestrated by dunder set adder, and del is a analogy to the dunder set. The key points here are that dunder get attribute, dunder set attribute, dunder del attribute, these are the outer layers. These are called on all attribute lookups. And so they orchestrate the lookup process, including calling the descriptor protocol. If you're going to implement a descriptor and you're going to be providing something that implements the descriptor protocol, this allows you to be a little more tactical on a per attribute basis versus all attributes. Writing your own descriptors, you might want to do it for data validation, lazy evaluation and caching, type validation, logging, unit conversion. Attribute aliasing is allowing the same piece of data to be accessed between two different attributes. They're sharing the same underlying storage. And ORM field definitions use this all over the place. A tip to hat to Hinnick, the author of Adders. He is using this all over the place. Wrapping up, whoa. This is all how it connects. I'm not going to read through that. The summary is descriptors are everywhere, and they are essential to how Python works. So hopefully you are coming away with an appreciation of that. And I am sure we are out of time for questions.
We are. I'm going to hit you with one question because you answered all of the rest of them
Okay.
in the end there. If you remove the entry from the dunder dict, would it revert to getting the default value? So when you had the
Yes.
descriptor, right, and you set the value.
Right, because it will go, because there's nothing in the dunder dict, it will then fall through to the non-data descriptor.
Very cool. All right. Let's give Scott a round of applause.
Thank you.
And I'm sure Scott's around to talk descriptors with you if you have more detailed questions, so feel free to hunt him down.
So in case you didn't notice, this is the link to the slides. In the slides is an appendice with all the code.